Are you winning, son?
Ada Philly.
Tony, if I got a calculator out and wrote 1 plus 2 plus 3 plus 4 plus 5, and I sat here until the end of everything and then pressed equals, would I get minus a
I
12?
actually mean the end of everything.
So I was scrolling through YouTube and YouTube decided to recommend to me number files video on sum of the natural numbers being equal to negative 12. Right, and this is a pretty famous sum. I've watched videos on it before. But for the most part, I didn't really think much of it. In the video, he mentioned that, apparently this is something that mathematicians do take seriously, and this is something that is used in higher level physics like string theory. And that's when I thought, that for example, there are lots of things in math that when you first come across, they don't really make much sense. So I remember when I came across imaginary numbers, that they are numbers that when you square, I is a number that when you square it, you get -1. Now this at that time didn't really make sense to me, because if there's a number, then it's if you multiply two same positive numbers, that's a positive number. If you multiply two same negative numbers, it's also a positive number. So it felt weird that I is some number that when you square it is -1. But over time you come across a lot of arguments or a lot of things that must be true, and then you eventually get your way around it, and you sort of understand. So for example, if you just let some number be root of -1, then if you square the root of -1, it is equal to -1, of course. So we can say that it is just some number which is not, well, frankly, a number that we know, in the sense that we know real numbers, we know their values. This is not a real number, but it is just some number that when you square it gives you -1. And there are lots of arguments for this. So for example, if it's a rule, you could call it a theorem or whatever it is, it's a rule of polynomials, that if you have a polynomial to the degree n, then it must have n roots. And this is something that is proved, and this is something that we know has to be true. But if complex numbers do not exist, then this is something that is not always true, and hence complex numbers must exist, right? But there are lots of these infinite series where you somehow do some pairing trick, or you somehow push something and it gives you something ridiculous. And this is still something that I have my reservations about. So for example, if so I'll first go over what is usually presented. The original proof of this has a lot of complex stuff, like the zeta function and all of those, but there's a simpler argument that's provided, that is, first we take a sum that is 1 minus 1 plus 1 minus 1, and all the way, and then we take some other sum which is 1 minus 2 plus 3 minus 4 all the way, right? And so first we need to calculate this. So s1, well, first thing we can notice is that if we take 1 minus s1, we would get 1 minus 1 minus 1 plus 1 minus 1 and all the way. Well, we realize that we actually get the same thing back. So this would be 1 minus 1 plus 1 minus 1 plus 1 minus, and so on. So in other words, this you get the same thing back, which is s1. So 1 minus s1 must equals s1. In other words, s1 equals half. So this thing 1 minus 1 plus 1, that is, you would notice that if you stop at an odd position, you get 0. Sorry, if you stop at an even position, you get 0. If you stop at an odd position, you get 1. But if you take them all the way to infinity, you apparently get half. And so now we can take a look at s2, which is 1 minus 2 plus 3 minus 4 and so on. Now if we do s2 plus s2, and the reason why I'm doing this is because I want to connect it to this, and there's a simple way of connecting this, is that if I take s2 like so, and then I take the other s2 but I shift it in this particular way, minus 4, then we can see that in the end 1 you would get 1, and then minus 1 plus 1 minus 1 plus 1, and this pattern would continue on, and this is something that we already know. In other words, 2s2 is equal to half, s2 is equal to 4, and so using these two results we can compute the sum of n natural numbers. So let's say s3 is equal to 1 plus 2 plus 3 plus 4 all the way to infinity. If we take the sum s3 minus s2, it will basically be well, you have the same 1 plus 2 plus 3 all the way to infinity, and then you have minus 1 plus 2 minus 3 plus 4 and all the way. In other words, the odd numbers are being cancelled out and the even numbers are being doubled. So you get 4 plus 8 and then so on. In other words, if we take 4 common, we would get 1 plus 2 plus 3 and all the way to infinity. In other words, what we get by factoring out the 4 is the same number as 3. So s3 minus s2 must equal s3. In other words, must equal 4 times s3. In other words, minus 1 over 4 is equal to 3 s3. s3 is hence equal to minus 1 over 12. And we are done. Now, this may seem like a convincing enough proof that all the things should cancel out, but there are a lot of problems with these. So for example, let's just first look at something that does make sense. Let's say we look at a convergent series. So a convergent series is a series that is a sum that would approach some value as you go on to infinity. So for example, if we take 1 plus 2 plus 3, if we take 1 plus half plus 1/4 plus 1/8 and so on. Now, if you actually try to compute this for some values, you would see that this is some number that is getting closer and closer to some value, and that value is actually equal to 2. And there are lots of ways to prove this. So we can notice that this is a geometric series in which the starting number is 1, the ratio is 2. In other words, the ratio is half. In other words, the sum to some n is equal to 1 multiplied with 1 minus half to the power n over 1 minus half. This is something that is pretty easy to prove. So we can take the limit as n approaches infinity. We can see that the limit as n approaches infinity, this would be 0. So in other words, we just have 1 minus 0, 1 minus half, which is equal to 2. And to also give you a nice little geometric proof, let's say you have some square which is 1 by 1. In other words, the area is 1, and then you take half of its length, so you get half. Let me draw a proper one. You get half and you get 1. In other words, the area is half, and then you take the half of this, in other words, which is 1/4, and then you take the half of this, 1/8, and you continue going on and on. What you will notice is that if you look at the big picture, this turns out to be a 2 by 1 rectangle whose area would be 2. And as you're going on and on, this certain gap that is being left is being closed down. So in other words, if you could go on to infinity, this would equal 2. So convergent series are something that makes sense because it must equal some number rather, because the values are getting smaller and smaller. Now, if we take a look at these two sums, or actually let me add s3 to 1 plus 2 plus 3 plus 4. So we computed that this equals half, we computed this equals 1/4, we computed this equals negative 1/12. Now, first of all, doesn't make any sense. All of these are a bunch of integers interacting with each other in only plus and minus. And as long as integers are only being added or subtracted, the value that you get has to be an integer. But we can see that all of these sums are indeed fractions, which does not, of course, make sense. If we take a look at s3, it does not make any more sense in a way that all the positive integers are being added. So you're adding a plus b, let's say, and both of them are positive, then the number that you get from adding a plus b should be a positive number c. Now, we saw the proof, so what is actually going wrong? What I think is that you can simply not assume that this thing that goes on to infinity will equal some number. We cannot assume that this equals some number either, or this equals some number. As long as the sum is not convergent, you cannot assume that it would equal some number. So what I'm trying to argue here is that if you have something which is 1 minus 1 plus 1 minus 1, and apparently it goes off to infinity, then this thing cannot equal some number. And of course, if you have something like 1 plus 2 plus 3 all the way to infinity, you cannot assume that this equals some number, because infinity is not something that is a number, it is something that is more of an idea. But if you treat infinity as a number, let's say you say that s equals infinity, then you would get lots of problems. So for example, infinity plus 1 is equal to infinity, because infinity is an idea rather than a number, and it's the idea that infinity is the largest number. So if you substitute this, you get s plus 1 equals s, in other words 1 equals 0, and you've broken math. So since these divergent series blow off to infinity, I don't think it's fair that we should put an equality sign here and say that, okay, this might equal some number. Because, okay, so let me give another argument for this. Let's say we have 1 plus 2 plus 3 plus 4 all the way to something, and this equals s. If I make a new series, let's say Sx, and I let Sx be minus 1, minus 1, minus 1, minus 1, and so on, so on. Now, I know that this would go off to negative infinity, but since apparently we are treating infinity as a number, I can say that this equals some number Sx. So, what I'm going to do is, I'm going to do S plus Sx, and it would be equal to 1 plus 2 plus 3 plus 4 dot dot dot, and then we would get minus 1 minus 1 minus 1 minus 1 dot dot dot. So the reason why I chose this specifically is because I wanted to get a result such that I get s back, and over here I am getting s back because now everyone is one value less, so I get 1 plus 2 plus 3 plus dot dot dot. In other words, this is also s. So we arrive at the conclusion that s plus sx is equal to s. Now this is only possible if sx equals 0, which again is nonsensical, that minus 1 minus 1 minus 1 minus 1 dot 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 equals 0. All the numbers are negative, it simply cannot be 0. So what I'm trying to argue here is that, in all of these proofs, we first assume that this equals some number s, or but whatever the letter you choose. But what I'm saying here is that this cannot equal some s simply because of the pattern that is going on. Like for example here, it cannot equal if you go on for infinity, it will just keep on oscillating between 1 and 0 and 1 and 0 and 1 and 0. In other words, it is not coming to some value. And for the same reason, we cannot say that this thing equals some value, because after every step your value keeps on increasing and you would go on to infinity. And with infinity, if you're treating it as a number, then that would be a problem, because infinity is not really a number. So I don't know, this is something that sort of still doesn't make sense to me. Well, that was the whole video. See you in the next.